On August 15, 1977, at exactly 23:16 Eastern Time, something extraordinary happened in a cornfield in Ohio. The Big Ear Radio Observatory detected a signal from space that would haunt scientists for decades. It lasted exactly 72 seconds, then it vanished forever. Jerry Amon was reviewing computer printouts the next morning when he spotted it. The signal was so strong, so clearly artificial, that he grabbed a red pen and scrawled, "Wow," in the margin. That handwritten exclamation became the most famous annotation in radio astronomy history. The wow signal came from the direction of Sagittarius, near the constellation's densest star fields. Its frequency was 1420.4556 MHz, a number that sent chills through anyone familiar with the search for extraterrestrial intelligence. This frequency represents the natural emission line of hydrogen, the most abundant element in the universe. If you were an alien civilization trying to communicate across the galaxy, you'd want to choose a frequency that any scientifically advanced species would recognize. Hydrogen's signature is universal. Every civilization that understands chemistry would know to look there. The signal's intensity was remarkable. It registered as 6EQUJ5 on the computer printout, peaking at U, which represented extraordinary power compared to cosmic background noise. But here's what made the wow signal truly mysterious. It appeared in only one of the Big Ear's two receivers. The telescope used two separate detection systems scanning the same patch of sky. If the signal had been continuous, both receivers should have detected it. Instead, only one registered the transmission, suggesting the signal lasted less than 3 minutes. The source location adds another layer of intrigue. Big Ear's computer calculated the signal originated from an empty region of space, with no bright stars or known cosmic phenomena nearby. Whatever transmitted the signal was either incredibly distant or incredibly powerful. Scientists have proposed numerous explanations over the decades. Maybe it was satellite reflection, though no known satellites were positioned correctly. Perhaps it came from Earth-based interference, though the frequency was protected for radio astronomy. Some suggested unknown natural phenomena, like new types of pulsars or stellar flares. The most tantalizing possibility remains unspoken in many scientific papers, but whispered in observatory cafeterias worldwide. What if the wow signal was exactly what it appeared to be? A directed transmission from another civilization, perhaps trying to make contact with anyone listening in our cosmic neighborhood. The signal's brief duration could support this hypothesis. If an alien civilization were broadcasting in all directions, we might only intercept their signal for the few minutes it takes their rotating transmission beam to sweep past Earth. Attempts to relocate the signal have failed repeatedly. Astronomers have pointed radio telescopes at the same patch of sky hundreds of times since 1977, using more sensitive equipment and longer observation periods. The silence has been absolute. This failure doesn't necessarily debunk the alien hypothesis. Advanced civilizations might use efficient targeted transmissions rather than continuous broadcasts. They might send periodic signals on schedules spanning years or decades. 46 years later, Jerry Amon's red pen mark remains the closest we've come to intercepting a message from the stars. The months following the wow signal's discovery transformed into one of astronomy's most intensive searches. Scientists knew they had detected something unprecedented, but proving its origin required the one thing they couldn't achieve: making it happen again. John Krause, the Big Ear Observatory director, immediately organized follow-up observations. Within weeks, multiple radio telescopes were scanning Sagittarius. The Arecibo Observatory in Puerto Rico, the most sensitive radio telescope on Earth, joined the search. The Very Large Array in New Mexico dedicated observation time to the mysterious coordinates. The silence was deafening. Month after month, the targeted region produced nothing but cosmic background radiation. The hydrogen line frequency that had blazed with artificial intensity for 72 seconds returned to its natural, barely detectable whisper. This non-repetition actually strengthened the signal's mystery. Natural cosmic phenomena tend to be either continuous or regularly periodic. Pulsars flash with clockwork precision. Quasars maintain steady output over years. Solar flares create detectable afterglows that fade gradually. The wow. Signal did none of these things. It appeared once, blazed brightly, and vanished completely. This behavior matches theoretical predictions for artificial transmissions better than known natural phenomena. Radio astronomers developed techniques for distinguishing artificial signals from cosmic noise. Artificial transmissions typically show narrow bandwidth, concentrating energy in tight frequency ranges. They often originate from point sources, rather than extended regions. Most importantly, they sometimes show Doppler shift patterns indicating transmission from planetary surfaces or orbiting spacecraft. The wow! Signal displayed many artificial characteristics. Its bandwidth was remarkably narrow, concentrated almost entirely within a few hertz around the hydrogen frequency. The source appeared to be a single point rather than an extended cosmic structure. However, the signal's brief duration prevented detailed analysis. 72 seconds provides enough time to confirm detection, but insufficient data to definitively separate artificial transmission from exotic natural phenomena. The statistical challenge became apparent as searches continued. If aliens were transmitting targeted beams across the galaxy, Earth might intercept such signals only rarely and briefly. A civilization using efficient narrow beam transmissions might sweep past our location once every few years or decades. This realization led to new search strategies. Rather than expecting immediate repetition, astronomers began long-term monitoring programs designed to catch periodic signals with extended cycles. Projects like SETI at home distributed computing power across millions of computers, analyzing radio telescope data for patterns emerging over years. The emotional toll on researchers became significant. Many astronomers privately believed the wow signal represented genuine contact, but scientific methodology demanded reproducible evidence. The inability to relocate the detection created frustrating limbo between discovery and confirmation. Alternative explanations emerged as searches continued. Some scientists proposed that Earth-based interference might have created the signal through unknown propagation effects. Others suggested previously unknown natural phenomena involving exotic stellar physics or interplanetary plasma interactions. None of these explanations fully accounted for the signal's characteristics. Earth-based interference couldn't easily explain the precise hydrogen frequency selection. Natural phenomena typically produce broader spectral signatures than the wow signal's razor-sharp bandwidth. Modern SETI researchers have learned to live with this uncertainty. The wow signal established both the promise and frustration of radio searches for extraterrestrial intelligence. It proved that artificial-looking signals can reach Earth from interstellar space, but demonstrated how difficult such signals are to confirm through repetition. The silence after the storm continues, but it's now informed silence, shaped by knowledge that the universe might indeed be trying to communicate. In 2007, astronomers discovered something that made the wow signal look tame by comparison. Fast radio bursts, or FRBS, are cosmic explosions of radio energy so powerful they can outshine entire galaxies for milliseconds. They arrive from deep space with clockwork precision, then vanish without explanation. Some repeat on schedules that seem almost intentional. The first FRB was found by accident, buried in old data from Australia's Parkes Radio Telescope. Graduate student David Narkovich spotted a brief spike of radio energy that didn't match any known cosmic phenomenon. The burst lasted just 5 milliseconds but released more energy than the Sun produces in 3 days. What made this extraordinary wasn't just the burst's power, but its location. The radio waves had traveled billions of light years to reach Earth, originating from a galaxy so distant that its light began the journey when the universe was less than half its current age. Within years, radio telescopes worldwide began finding more FRBS. Each detection revealed new puzzles. The bursts showed dispersion patterns indicating passage through vast amounts of intergalactic plasma. Their radio signatures bore no resemblance to known stellar explosions or black hole collisions. The mystery deepened when astronomers discovered repeating FRBS. Unlike most bursts, which appeared once and never repeated, some sources began producing multiple flashes across months or years. FRB 121102 became the first confirmed repeater, generating dozens of detectable bursts from the same cosmic location. The repetition patterns defied easy explanation. Natural explosions typically occur once, like supernovas or gamma-ray bursts. Repeating phenomena usually show regular periodicity, like pulsars spinning with mathematical precision. But repeating FRBS followed irregular schedules that seemed random yet somehow structured. FRB 180916.J0158+65 provided the most intriguing example. This source produces bursts in clusters separated by quiet periods lasting exactly 16.35 days. The precision suggests an orbital mechanism, perhaps involving a neutron star orbiting a massive companion. But the energy requirements still exceed what known astrophysics can easily explain. Some fast radio bursts show additional mysterious properties. Their radio pulses are highly polarized, indicating passage through extremely strong magnetic fields. The frequency patterns suggest the sources are surrounded by dense plasma clouds. A few bursts arrive with subtle frequency modulations that almost resemble encoded information. The possibility of artificial origins has been seriously discussed in peer-reviewed journals. The energy scales would require technology far beyond human capabilities, but they fall within theoretical limits for civilizations capable of harnessing stellar power. Such civilizations might use FRB-like transmissions for interstellar communication or spacecraft propulsion systems. Natural explanations remain more widely accepted. Magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, can produce intense radio bursts through magnetic reconnection events. Some theoretical models suggest that highly magnetized neutron stars could generate FRB-like emissions during starquakes or magnetic pole reversals. Recent discoveries have complicated natural interpretations. FRB 202-00120e was detected in a nearby galaxy, allowing detailed study of its environment. The burst originated from a globular cluster containing ancient stars billions of years old. Such old stellar populations shouldn't contain the young, massive neutron stars that most FRB models require. Current estimates suggest these bursts occur thousands of times per day across the observable universe. If they represent natural phenomena, then the cosmos contains explosive processes far more common and energetic than previously suspected. Like the WOW signal before them, FRBS represent cosmic mysteries that challenge our understanding while offering tantalizing hints about the universe's hidden complexities. Deep in the radio spectrum, at exactly 1,420.405,751 MHz, lies what astronomers call the most important frequency in the universe. This is the 21-centimeter line, the natural emission signature of hydrogen atoms transitioning between energy states. If aliens exist and want to communicate across the galaxy, this is where they would likely choose to call. The physics is elegantly simple. Hydrogen consists of one proton and one electron. Occasionally, the electron flips its spin orientation relative to the proton, releasing energy as a radio photon. This transition produces radiation at exactly 21 centimeters wavelength, corresponding to 1,420 megahertz. Any species that understands basic chemistry would recognize hydrogen's signature. It's universal, unavoidable, and fundamental to stellar physics. Unlike arbitrary cultural references that might vary between species, hydrogen's emission line represents a constant throughout the galaxy. The frequency sits within what radio astronomers call the water hole, a remarkably quiet region bounded by hydrogen and hydroxyl radical emissions. Between these natural markers lies a cosmic silence zone where few natural phenomena produce strong radio signals. It's as if the universe provided a dedicated communication channel. Giuseppe Cocconi and Philip Morrison first proposed this concept in their 1959 Nature paper. They reasoned that any technological civilization would eventually discover radio astronomy and recognize the hydrogen line's significance. It would serve as a natural meeting point, a galactic telephone frequency that every scientifically advanced species would monitor. Modern SETI programs have embraced this logic while expanding search parameters. The Breakthrough Listen initiative monitors millions of nearby stars across waterhole frequencies, using advanced signal processing to detect artificial transmissions against cosmic background noise. The challenge lies in the sheer scale of possibilities within even this restricted frequency range. The waterhole spans several megahertz, containing millions of potential communication channels. Add factors like Doppler shifts from planetary rotation and orbital motion, and the search space becomes astronomical. Recent discoveries have complicated the hydrogen highway hypothesis. Fast radio bursts and other exotic phenomena produce intense signals across wide frequency ranges, including the supposedly quiet waterhole region. These natural events demonstrate that the universe can generate powerful artificial-looking signals through purely physical processes. Additionally, advanced civilizations might deliberately avoid obvious frequencies to prevent detection by less developed species. They might use sophisticated encoding schemes that spread signals across multiple frequencies or embed information in seemingly natural emissions. Despite these complications, the 21-centimeter line remains central to SETI strategy. The frequency represents our best guess about where aliens might choose to communicate, based on fundamental physics rather than cultural assumptions. Every major radio telescope on Earth monitors this frequency, waiting for the artificial signal that could change our understanding of our place in the universe. The search continues along the hydrogen highway, driven by compelling logic that any civilization capable of interstellar communication would recognize the same physical constants that guide our own radio astronomy. Whether that assumption proves correct remains one of the greatest questions in science. The hydrogen line offers our most logical starting point for cosmic conversation, a frequency where minds separated by light years might finally connect through the universal language of physics. The silence we encounter there might reflect the rarity of technological civilizations, or it might simply mean we haven't been listening long enough in a universe where cosmic conversations unfold across geological timescales. In 1995, the most comprehensive search for extraterrestrial intelligence ever attempted began scanning the cosmos with unprecedented precision. Project Phoenix represented the culmination of decades of SETI research, targeting nearby sun-like stars with technology sensitive enough to detect alien transmissions weaker than signals from a typical cell phone. The project emerged from the ashes of NASA's cancelled SETI program, which Congress had terminated in 1993 amid budget pressures. Private funding from tech entrepreneurs and the SETI Institute allowed Phoenix to rise from this setback, using the world's largest radio telescopes for targeted searches that government funding could no longer support. Project Phoenix's strategy differed fundamentally from previous SETI efforts. Rather than scanning random patches of sky, the project focused on carefully selected star systems within 200 light-years of Earth. Each target star resembled our Sun in mass, age, and spectral type, theoretically increasing the likelihood of finding planets capable of supporting technological civilizations. The target selection revealed the complexity of searching for alien intelligence. Stars too young might not have allowed sufficient time for life to evolve. Stars too old might have exhausted their fuel or experienced catastrophic events. Binary star systems presented gravitational complications that could disrupt planetary formation. Phoenix used a sophisticated two-telescope confirmation system to eliminate false positives. When the primary telescope detected an interesting signal, computers automatically directed a second telescope to verify the detection. True extraterrestrial signals should appear at both locations simultaneously, while terrestrial interference would typically affect only one telescope. This dual telescope approach proved essential for filtering out the constant barrage of human-generated radio interference. Modern civilization bathes our planet in electromagnetic radiation from cell phones, satellites, and radar systems. Distinguishing alien signals from this electronic cacophony requires techniques that eliminate terrestrial contamination while preserving potential extraterrestrial transmissions. The project's sensitivity reached extraordinary levels. Phoenix could detect transmissions as weak as 10 to the minus 26 watts per square meter, equivalent to receiving a 1,000-watt transmitter signal from the nearest star. This capability meant that alien civilizations using technology only slightly more advanced than our planetary radar systems would be detectable across interstellar distances. Over 8 years, Project Phoenix examined nearly 800 star systems, accumulating thousands of hours of observation data. The search covered frequencies from 1200 to 3000 megahertz, encompassing the waterhole region, while extending into adjacent bands, where alien transmissions might occur. The results were simultaneously encouraging and disappointing. Phoenix detected millions of signals during its operation, but every single detection ultimately traced back to terrestrial sources. Satellites, aircraft, and ground-based transmitters created a constant stream of false alarms that required painstaking investigation to eliminate. Several signals generated significant excitement before revealing mundane explanations. Narrow-band emissions from promising star systems would trigger confirmation protocols, only to disappear when the second telescope searched the same coordinates. These phantom signals typically resulted from satellite passes or atmospheric effects. The absence of confirmed alien signals led to important insights about technological civilizations. Either such civilizations are extremely rare in our galactic neighborhood, or they use communication technologies fundamentally different from radio broadcasts. Project Phoenix established detection limits that constrain theories about alien communication. Any civilization within 200 light-years using radio technology comparable to human capabilities should have been detected. The silence implies that such civilizations either don't exist in our cosmic neighborhood or have moved beyond radio communication. The search for extraterrestrial intelligence remains a process of systematic elimination, ruling out natural explanations until only artificial intelligence remains possible. The universe is full of radio voices that sound almost intelligent but aren't. These cosmic mimics have fooled astronomers repeatedly, creating false alarms that illuminate both the challenges of searching for alien signals and the surprising creativity of natural phenomena in generating patterns that seem artificially designed. The most famous case occurred in 1967 when Jocelyn Bell Burnell discovered the first pulsar. The signal appeared as regular radio pulses occurring every 1.337 seconds with clockwork precision. The consistency was so remarkable that the Cambridge research team briefly considered extraterrestrial origins, even designating the source LGM-1 for Little Green Men. The regularity initially defied natural explanation. No known cosmic phenomenon could produce such precise timing over extended periods. The pulses showed no Doppler shifts, indicating orbital motion, suggesting a stationary source of enormous stability. Only after discovering multiple pulsars did astronomers realize they were observing neutron stars, collapsed cores of massive stars that had exploded as supernovas. These extraordinarily dense objects rotate rapidly while emitting beams of radio waves from their magnetic poles. Like cosmic lighthouses, they sweep these beams across space. Pulsars taught SETI researchers crucial lessons about distinguishing artificial signals from exotic natural phenomena. True alien transmissions would likely show characteristics that pulsars lack: information content, frequency variation, or deliberate modulation patterns that convey meaning beyond simple periodic timing. More recent discoveries have created new categories of radio imposters. Fast radio bursts initially seemed so artificial that some astronomers seriously proposed extraterrestrial origins. The enormous energies and precise burst characteristics suggested technology operating on galactic scales, possibly alien communications or spacecraft propulsion systems. The periton signals provided another cautionary tale about terrestrial interference masquerading as cosmic phenomena. These mysterious radio bursts appeared to originate from various directions in space, showing dispersion characteristics that suggested astronomical distances. For years, they puzzled radio astronomers who couldn't identify any natural process that could produce such signals. The solution proved embarrassingly mundane. Peritons were generated by microwave ovens at the observatory facility, specifically when ovens were opened before their heating cycles completed. The microwave radiation leaked into telescope systems, creating signals that appeared to come from deep space, but actually originated in the observatory kitchen. This discovery highlighted the persistent challenge of eliminating terrestrial interference from SETI observations. Modern civilization generates radio emissions across virtually every frequency band, creating constant background artificial signals that can mimic extraterrestrial transmissions. The WOW! Signals failure to repeat demonstrates another category of radio ghost. Some cosmic phenomena produce brief, intense emissions that occur only once or at irregular intervals spanning years. Solar flares, gamma-ray bursts, and magnetar eruptions can generate radio signals with characteristics that superficially resemble artificial transmissions. Distinguishing between natural transients and alien signals requires analyzing multiple signal characteristics simultaneously. Artificial transmissions should show narrow bandwidth, consistent frequency, and possibly information content that natural phenomena cannot produce. However, the brief duration of most candidate signals prevents detailed analysis. Recent advances in machine learning have created new opportunities for identifying artificial signals among natural radio emissions. Algorithms trained on known interference patterns can automatically classify terrestrial contamination, while pattern recognition systems search for structured emissions that might indicate alien intelligence. The challenge remains formidable because advanced extraterrestrial civilizations might deliberately design transmissions to appear natural, either to avoid detection by hostile civilizations or to embed information within seemingly normal cosmic emissions. Radio astronomy continues revealing new categories of cosmic phenomena that generate structured emissions previously thought impossible through natural processes. In September 2015, citizen scientists examining data from NASA's Kepler Space Telescope stumbled upon something that would challenge our understanding of stellar physics and ignite speculation about alien megastructures. KIC 8462852, a star 1,400 light-years away in Cygnus, was dimming in ways that shouldn't be possible according to everything we know about how stars behave. The discovery came through Planet Hunters, a crowdsourced project where volunteers examine stellar brightness data to identify planets crossing in front of their host stars. These planetary transits create predictable dimming patterns, small, regular dips that repeat with orbital precision. But KIC 8462852 showed nothing like this orderly behavior. Instead, the star displayed bizarre, irregular dimming events that sometimes blocked up to 22% of its light. To put this in perspective, even Jupiter would block only 1% of the sun's light during a transit. Whatever was crossing in front of KIC 8462852 was enormous and oddly shaped. The dimming patterns defied conventional explanation. They showed no periodicity, no regular timing that would suggest orbiting planets. The dips varied dramatically in depth and duration, some lasting hours, others persisting for days. The shapes were asymmetric, with steep drop-offs followed by gradual recoveries. Tabitha Boyajian, the Yale astronomer who led the analysis, found herself confronting data that challenged fundamental assumptions about stellar systems. Natural phenomena typically create symmetric, predictable patterns. Planets orbit with clockwork regularity. Even cometary debris follows predictable orbital mechanics. The star, quickly nicknamed Tabby's star, became subject to intense scrutiny. follow-up observations revealed additional mysteries. The unusual dimming appeared in historical data spanning over a century, suggesting whatever caused them was long-lasting and substantial. More disturbing, the stars seemed to be gradually dimming over decades. Analysis of photographic plates from Harvard's archives showed a steady decline in brightness of about 14% between 1890 and 1990. This long-term fading, combined with dramatic short-term dimming events, painted a picture of unprecedented stellar system changes. Natural explanations struggled to account for these observations. A swarm of comets might create irregular dimming, but the scale required seemed implausible. Dust clouds from planetary collisions could theoretically produce such effects, but the required debris would heat up and emit infrared radiation that wasn't observed. The failure of conventional explanations led to more exotic theories. Perhaps the star was consuming a planet, creating debris clouds that periodically obscured its light. Maybe we were witnessing collision aftermath between large asteroids or moons. But the most captivating explanation came from Jason Wright at Penn State University, who suggested that artificial structures might be responsible. Advanced extraterrestrial civilizations might construct massive arrays of solar collectors around their stars, harvesting energy on scales beyond human comprehension. These hypothetical Dyson spheres would consist of countless individual collectors orbiting a star in complex configurations. Such megastructures would create exactly the kind of irregular, dramatic dimming patterns observed in Tabby's star. The lack of infrared excess radiation might indicate highly efficient energy conversion. The alien megastructure hypothesis generated worldwide attention, transforming an obscure stellar anomaly into a cultural phenomenon. Radio telescopes trained their receivers on the system, searching for artificial signals that might accompany such advanced technology. The results were negative. Subsequent observations have provided more conventional explanations for some behaviors. Analysis of the star's color during dimming events revealed signatures consistent with dust rather than solid objects. The century-long dimming might result from natural stellar variability. However, the mystery remains partially unsolved. While dust clouds can explain many observations, the source and behavior of this dust continues to puzzle astronomers. In 1960, theoretical physicist Freeman Dyson published a paper that would forever change how we think about advanced civilizations and their energy needs. His radical proposal suggested that sufficiently developed alien species would eventually surround their stars with massive structures designed to capture and utilize every photon of available energy. Dyson's reasoning was elegantly simple. All technological civilizations require energy to power their activities, and energy consumption grows exponentially as they advance. Eventually, even planetary resources become insufficient. The logical next step would be to harvest their star's enormous energy output directly. Our sun produces about 400 trillion watts of power continuously. More energy every second than human civilization has consumed throughout its entire history. A sphere of solar collectors surrounding our star could capture this entire output, providing energy resources that would enable technological capabilities beyond current imagination. Such a structure wouldn't necessarily be a solid shell. Dyson envisioned swarms of individual collectors orbiting the star in complex patterns. These components might be solar panels, manufacturing facilities, habitats, or technologies we can't conceive. The key feature would be their collective ability to intercept and utilize stellar energy on astronomical scales. The observable signatures of such megastructures would be distinctive and detectable across interstellar distances. A Dyson sphere would absorb its star's visible light and re-radiate that energy as infrared heat. To distant observers, the star would appear unusually dim in visible light while showing excess infrared emission. Modern astronomy has developed sophisticated techniques for detecting these infrared anomalies. Space telescopes have catalogued thermal emissions from millions of stars, searching for excess heat that might indicate artificial energy collection systems. Several candidates have emerged, showing infrared properties that don't quite match natural stellar evolution models. The most intriguing candidates are red giant stars with circumstellar dust shells that seem too structured and long-lived to result from natural stellar mass loss. These systems show infrared signatures consistent with solid material, organized in regular patterns around the central star. The energy scales involved in Dyson sphere construction challenge our understanding of technical feasibility. Building such structures would require disassembling entire planets to provide raw materials, then organizing those materials into precisely engineered orbits. The logistics would demand technologies that could manipulate matter and energy on stellar scales. However, the potential rewards justify such enormous undertakings. A civilization with access to their star's complete energy output could undertake projects that seem impossible today. Interstellar travel, planetary engineering, massive computer systems, or attempts to influence stellar evolution and extend their star's lifetime. The Kardashev scale provides a framework for classifying civilizations based on energy consumption. Type 1 civilizations harness all available energy from their home planet. Type 2 civilizations, like those building Dyson spheres, utilize their entire star's output. Type 3 civilizations would control entire galaxies' energy resources. Current human civilization ranks at approximately 0.7 on this scale, still dependent on fossil fuels and unable to capture even our planet's complete energy budget. The leap to Type 2 capabilities would represent a technological advancement as significant as entire human development history. Critics point out potential flaws in underlying assumptions. Advanced civilizations might develop energy sources that don't require stellar collection, fusion reactors, antimatter production, or exotic physics that taps quantum vacuum energy. They might also discover fundamental limits to energy consumption that make stellar-scale collection unnecessary. The search for Dyson spheres continues through projects that systematically analyze infrared catalogs for anomalous objects. Machine learning algorithms scan millions of stellar spectra, identifying candidates that show infrared excess without obvious natural explanations. Whether we ever detect genuine Dyson spheres or not, the concept has transformed thinking about the relationship between technology and energy. Just over 4 light-years away, orbiting our nearest stellar neighbor, lies the closest potentially habitable planet we know of. Proxima Centauri b sits in its red dwarf star's habitable zone, where liquid water might exist. In 2019, radio telescopes detected something unexpected coming from that direction, a narrow-band signal that looked disturbingly artificial. The detection came through Breakthrough Listen, the most comprehensive search for extraterrestrial intelligence ever conducted. Using the Parkes Radio Observatory in Australia, scientists were monitoring Proxima Centauri when their automated systems flagged an unusual transmission at 982.002 MHz. The signal appeared only when the telescope pointed toward Proxima and vanished when it looked elsewhere. What made this signal extraordinary wasn't just its apparent origin near our nearest neighbor star, but its characteristics. The transmission was incredibly narrow in bandwidth, concentrated in a frequency range of less than 5 Hz. Natural radio sources typically spread their energy across much wider frequency ranges. This focused emission looked exactly like the artificial signal that SETI researchers had been seeking. The signal, designated BLC1 for Breakthrough Listen Candidate 1, showed another suspicious property. It drifted in frequency over time. This drift appeared consistent with transmission from a rotating planet, where radio transmitters would create subtle Doppler shifts as they moved toward and away from Earth. The pattern matched theoretical predictions for signals originating from planetary surfaces. Project scientists spent months analyzing BLC1 with extreme caution. The history of SETI includes numerous false alarms, where natural phenomena or terrestrial interference initially appeared to be alien signals. The team applied rigorous verification procedures, checking for satellite interference, telescope artifacts, and coincidental timing with Earth-based transmissions. The signal's proximity to Earth made its implications staggering. If BLC-1 truly originated from the Proxima Centauri system, it would represent the first confirmed detection of extraterrestrial technology. Radio telescopes worldwide would immediately target the system for follow-up observations. However, red flags gradually emerged during analysis. The signal appeared in multiple observation sessions, but not consistently. Some observations showed the transmission clearly, while others recorded only cosmic background noise. True planetary signals should be more persistent, varying only due to planetary rotation and orbital motion. More troubling, careful analysis of observation timing revealed correlations with human activity. The signal appeared most strongly during working hours at the park's observatory and showed suspicious timing relationships with telescope maintenance activities and personnel schedules. The breakthrough came when researchers identified the actual source: radio frequency interference from electronic equipment at the observatory site. Specifically, the signal originated from a computer system used to monitor telescope operations. The equipment generated narrow-band radio emissions that leaked into the telescope's receivers through subtle coupling effects. The illusion of extraterrestrial origin resulted from coincidental timing. The interfering equipment operated only during certain periods, creating the appearance of a signal that came and went mysteriously. The frequency drift that had seemed so compelling as evidence of planetary motion actually resulted from thermal effects in electronic oscillators. BLC-1's debunking provided valuable lessons for SETI methodology. Even sophisticated search programs remain vulnerable to subtle forms of radio frequency interference that can mimic extraterrestrial signals with remarkable fidelity. The case demonstrated the importance of exhaustive verification procedures. The episode also highlighted unique challenges of searching for signals from nearby stars. Proxima Centauri's proximity makes it attractive for SETI observations, but this same proximity means that any signals would be relatively strong and therefore more likely to be confused with terrestrial interference. Despite BLC-1's mundane explanation, the search for signals from Proxima Centauri continues. The system remains one of the highest priority targets due to its proximity and confirmed presence of a potentially habitable planet. Deep in stellar catalogues lie worlds so bizarre that their very existence challenges our understanding of planetary formation. These cosmic anomalies orbit too close to their stars, spin in impossible directions, or possess atmospheric compositions that seem almost engineered. Each discovery forces astronomers to expand theories about what's possible in planetary systems. Hot Jupiters represent perhaps the most dramatic challenge to our solar system-centric view. These gas giant planets orbit their stars closer than Mercury orbits our Sun, completing full orbits in days or hours. Their existence was so unexpected that first discoveries were initially dismissed as observational errors. The physics of hot Jupiter formation defies simple explanation. Gas giants require vast amounts of hydrogen and helium to form, materials that can only accumulate in cold outer regions of protoplanetary disks. Yet hot Jupiters orbit so close that these volatile materials should have been blown away during system formation. The leading explanation involves planetary migration, where gravitational interactions with protoplanetary disks cause newly formed gas giants to spiral inward toward their central star. This migration can transport planets from formation zones to scorching orbits. However, the details remain poorly understood. Some hot Jupiters show even more puzzling characteristics. WASP-12 B orbits so close that the planet is being torn apart by tidal forces, creating a trailing stream of atmospheric material. The planet's dayside temperature exceeds 2,500 degrees Celsius, hot enough to vaporize most known materials and create atmospheric chemistry that resembles stellar interiors. Retrograde planets add another layer of impossibility. These worlds orbit their stars in the opposite direction from stellar rotation, violating basic expectations that planets should form from rotating disks that preserve angular momentum. HAT-P7b, WASP-17b, and several other confirmed retrograde planets challenge fundamental assumptions about planetary system formation. The retrograde motion suggests violent histories involving gravitational interactions that completely disrupted original system architecture. Close encounters with other stars, interactions with massive planetary companions, or collisions between planetary embryos might flip entire orbits. However, the frequency exceeds what these rare events should produce. Ultra-short period planets push boundaries of what constitutes a planet versus stellar material. These worlds complete orbits in less than one Earth day, racing around their stars at velocities approaching 400 kilometers per second. The gravitational and tidal forces should tear apart any solid body, yet dozens have been confirmed. KOI 55. B orbits its host star every 5.8 hours at a distance where surface temperatures exceed 7,000 degrees Celsius. The planet appears to be solid rocky world, despite conditions that should vaporize any known planetary material. Its survival suggests either exotic material properties or formation mechanisms that differ fundamentally from standard models. The atmospheric compositions of some exoplanets seem almost deliberately engineered. HD 209458b shows atmospheric layers with precisely stratified chemistry that efficiently absorbs and redistributes stellar energy. The temperature distribution shows patterns that suggest active atmospheric circulation systems operating with remarkable efficiency. Some planets display atmospheric chemistry that appears to violate thermodynamic equilibrium. WASP 96b shows water vapor signatures that require specific temperature and pressure conditions to maintain stability, yet the planet's other atmospheric components suggest different thermodynamic states. Magnetic field measurements reveal impossible configurations. Some worlds generate magnetic fields thousands of times stronger than Earth's, despite lacking the metallic cores necessary for dynamo generation. Others show magnetic field orientations that don't align with planetary rotation. The orbital characteristics of multi-planet systems sometimes display mathematical relationships that seem too precise to result from natural gravitational evolution. The TRAPPIST-1 system contains 7 Earth-sized planets locked in a complex resonance chain where orbital periods follow exact mathematical ratios. These planetary anomalies might represent extreme examples of natural processes operating under conditions we rarely observe in our own solar system. Earth sits in what astronomers call the Goldilocks zone. Not too hot, not too cold, but just right for liquid water to exist on planetary surfaces. As we discover thousands of exoplanets, this habitable zone has become the holy grail of planet hunting. Yet the more we learn about true habitability, the more we realize how extraordinarily rare Earth-like conditions might be. The basic concept seems straightforward. Every star has a range of orbital distances where planets receive just the right amount of energy to maintain liquid water. Too close, and water boils away. Too far, and it freezes solid. This habitable zone depends on stellar luminosity, with hot stars having distant zones and cool stars having zones much closer. But real habitability involves far more complex factors than simple temperature calculations. Planetary atmospheres dramatically alter surface conditions through greenhouse effects, cloud formation, and circulation patterns. Venus sits technically within our Sun's habitable zone, yet surface temperatures exceed 460 degrees Celsius due to runaway greenhouse effects. Mars provides another cautionary example. The red planet orbits near the outer edge of our Sun's habitable zone, and geological evidence suggests it once possessed liquid water. However, Mars lost most of its atmosphere over geological time, probably due to its weak magnetic field, allowing solar wind to strip away atmospheric gases. The requirements for maintaining habitability over billions of years reveal additional complications. Stellar evolution causes stars to gradually brighten as they age, shifting habitable zones outward over time. Earth's continued habitability requires atmospheric regulation mechanisms that compensate for increasing solar luminosity. Planetary magnetic fields appear crucial for long-term habitability, protecting atmospheres from stellar wind erosion and shielding surface biology from harmful radiation. Earth's magnetic field results from convection in our planet's molten iron core. a process that requires specific conditions of planetary size, composition, and thermal evolution. The role of large moons in maintaining planetary habitability has become increasingly apparent. Our unusually large moon stabilizes Earth's axial tilt, preventing extreme climate variations that would result from chaotic wobbling. The moon also drives tidal forces that may have been crucial for early life's transition from ocean to land. Most exoplanets in habitable zones orbit red dwarf stars, which present unique challenges. These cool, long-lived stars have habitable zones so close that planets are likely tidally locked, with one hemisphere permanently facing the star and the other in eternal darkness. Such temperature differences could prevent atmospheric circulation and liquid water stability. Red dwarf stars also produce frequent stellar flares that could strip away planetary atmospheres or sterilize surface environments with intense radiation. Proxima Centauri regularly produces flares that would deliver radiation doses lethal to most Earth life forms to any planets in its habitable zone. The atmospheric chemistry requirements extend beyond simple water stability. Life as we know it requires specific ratios of gases like oxygen, carbon dioxide, and nitrogen. Too much oxygen creates fire hazards and toxic conditions. Too little prevents complex metabolism. The delicate atmospheric balance might be extremely difficult to achieve and maintain. Recent discoveries have revealed additional factors affecting habitability. The galactic location of star systems influences cosmic ray exposure, supernova frequencies, and heavy element abundances that affect planetary composition. Earth's position in the galaxy's habitable zone may be as important as its position around our Sun. The timing of planetary formation relative to galactic chemical evolution also matters. Early generations of stars lacked heavy elements necessary for rocky planet formation. Life might only be possible around stars that formed after sufficient heavy element enrichment. Climate modeling of potentially habitable exoplanets reveals how easily atmospheric conditions can become inhospitable. Small changes in composition, orbital characteristics, or stellar radiation can trigger runaway greenhouse effects or atmospheric collapse. These discoveries paint habitability as an extraordinarily delicate balance requiring multiple favorable conditions to align simultaneously. High above Saturn's North Pole, something impossible spins in perfect geometric precision. The hexagonal storm system measures 30,000 kilometers across, with sides longer than Earth's diameter, maintaining sharp angular boundaries that seem to defy atmospheric physics. This six-sided structure has persisted for decades, raising questions about whether natural processes can create such geometric perfection. The hexagon was first detected by Voyager spacecraft in the 1980s, but Cassini revealed its true complexity. The structure consists of a high-speed jet stream flowing at nearly 500 kilometers per hour, somehow maintaining perfectly straight sides and precise 60-degree angles. Computer models struggle to explain how geometric regularity can emerge from chaotic atmospheric turbulence. Laboratory experiments have created similar hexagonal patterns in rotating fluids under specific conditions, suggesting Saturn's polar hexagon might result from interactions between atmospheric circulation and rapid rotation. However, the scale and persistence exceed anything reproducible in terrestrial laboratories. The hexagon's geometric perfection has inspired more exotic theories. Some researchers have proposed that the structure might indicate atmospheric engineering projects, possibly artificial manipulation of Saturn's circulation patterns by advanced civilizations. While purely speculative, they highlight how even natural explanations require extraordinary physics. Earth's moon presents its own collection of anomalies that have fueled speculation about artificial origins. The moon's size relative to Earth is unprecedented among rocky planets in our solar system. Most planetary satellites are either tiny captured asteroids or formed through completely different processes than the collision scenario that supposedly created our moon. The moon's perfectly circular orbit and synchronous rotation, which keeps one face permanently toward Earth, seem almost engineered for optimal viewing from our planet. The odds that random collision debris would create such a geometrically perfect satellite system appear extraordinarily low. During Apollo missions, seismic measurements revealed that the Moon rings like a bell when struck by meteorites or spacecraft components. The seismic waves propagate through the lunar interior in ways that suggest hollow spaces or compositional discontinuities that don't match standard formation models. The Moon's surface geology shows unusual concentrations of heavy elements like titanium in locations inconsistent with natural differentiation processes. Some lunar rock samples contain metal alloys that require high-temperature formation conditions not expected in the Moon's formation environment. Iapetus, one of Saturn's moons, displays the most dramatically artificial-looking features in the solar system. The Moon's equatorial ridge extends for 1,300 kilometers, rising up to 20 kilometers above surrounding surface. This massive mountain range follows Iapetus's equator with uncanny precision, creating a structure that resembles a seam where two hemispheres might have been joined. The ridge's geometric perfection and unique location directly on Iapetus's equator challenge natural formation theories. Impact processes, volcanic activity, and tidal forces typically create irregular geological features that don't follow precise geometric patterns. Iapetus also shows dramatic brightness dichotomy, with one hemisphere covered in dark material, while the other remains bright and icy. This two-toned coloration follows precise boundaries that seem too sharp and regular for natural processes. Some of Saturn's smaller moons display orbital characteristics that seem artificially maintained. Several moonlets orbit within the planet's ring system at positions that shepherd gravitational interactions with ring particles. These orbital configurations require precise positioning that naturally tends to decay over time. The ring systems themselves show structure that challenges current understanding. The Cassini division, a gap in Saturn's rings, maintains sharp edges that theoretical models suggest should blur over time due to gravitational perturbations. Recent discoveries of artificial-looking structures around other planets have expanded these mysteries beyond our solar system. Some exoplanets show transit signatures that suggest ring systems with geometric regularities that exceed what natural ring formation should produce. While natural explanations exist for most phenomena, the geometric precision and long-term stability push boundaries of what standard physics can easily explain. On October 19, 2017, astronomer Rob Werrick spotted something unprecedented in telescope data from Hawaii's Panoramic Survey Telescope. Moving through the inner solar system at impossible speed was an object unlike anything in our catalogue. Its hyperbolic trajectory proved it came from interstellar space, making it the first confirmed visitor from another star system. The object, designated Oumuamua, using the Hawaiian word for messenger from afar, defied every expectation about interstellar visitors. Instead of the roughly spherical shape typical of asteroids or fuzzy coma of comets, Oumuamua appeared as an elongated, tumbling needle racing through space at nearly 90,000 kilometers per hour. Size estimates revealed extraordinary geometry. The object stretched at least 400 meters long, while measuring only 40 meters wide, creating an aspect ratio of 10:1, or possibly more extreme. No natural object in our solar system displays such needle-like proportions. Oumuamua's surface reflectivity added to the mystery. The object appeared unusually bright and reddish, reflecting sunlight in ways that didn't match typical asteroid compositions. The spectral characteristics suggested a surface covered in organic compounds, modified by millions of years of cosmic radiation. As Oumuamua approached the Sun, astronomers expected to see characteristic signs of cometary activity, outgassing, coma formation, and tail development as solar heating sublimated surface ices. Instead, the visitor remained stubbornly inactive, showing no signs of volatile materials. The absence of visible outgassing became puzzling when precise orbital measurements revealed that Oumuamua was accelerating away from the Sun faster than gravity alone could account for. The acceleration was tiny but measurable, about 1/10,000th of Earth's surface gravity, yet clearly present in multiple observations. This non-gravitational acceleration typically indicates cometary outgassing, where sublimating ice creates tiny rocket effects that alter orbital trajectories. But Oumuamua showed no visible signs of such activity. No coma, no tail, no spectroscopic evidence of gas or dust emission. Harvard astrophysicist Avi Loeb proposed a radical explanation. Oumuamua might be artificial. The object's extreme geometry resembled theoretical designs for light sails, ultra-thin structures that could be propelled by stellar radiation pressure. An interstellar probe using light sail technology would show exactly the non-gravitational acceleration observed. The light sail hypothesis explains several puzzling aspects. Radiation pressure acting on a thin, highly reflective surface could account for the acceleration without creating detectable emissions. The object's tumbling motion might result from attitude control problems in an ancient technological artifact. Critics pointed out that natural processes could potentially explain all observations. Oumuamua might be outgassing hydrogen, a nearly invisible gas that could create the acceleration without producing a visible coma. Alternatively, the object might represent a new class of interstellar body with properties unlike anything in our solar system experience. The hydrogen outgassing theory gained support from detailed modeling, showing that pure hydrogen emission could indeed create the observed acceleration while remaining below detection thresholds. However, this explanation required Oumuamua to contain substantial quantities of molecular hydrogen. As Oumuamua sped away from the inner solar system, radio telescopes searched for artificial signals that might confirm its technological nature. The Breakthrough Listen project monitored the object across multiple frequencies, looking for radio emissions that might accompany an active probe. The results were negative. The absence of radio signals didn't definitively rule out artificial origins. An inactive probe or technology using communication methods beyond our detection capabilities might remain radio silent while still representing alien engineering. Oumuamua's brief visit lasted only a few months before the object became too faint for detailed observation. By early 2018, it had vanished beyond our telescope's reach, carrying its secrets back into interstellar space. Whether natural phenomenon or artificial probe, the cigar from another star demonstrated that interstellar space contains objects stranger than our theories predicted. The physics of Oumuamua's motion through our solar system revealed characteristics that challenged fundamental assumptions about how objects behave in space. Its tumbling rotation, extreme velocity, and mysterious acceleration created a puzzle that continues to generate scientific controversy years after discovery. Spectroscopic observations revealed that Oumuamua was spinning chaotically, tumbling end over end with a rotation period of approximately 7.3 hours. This tumbling motion caused dramatic brightness variations, as different faces of the elongated object alternately caught and reflected sunlight. The tumbling rate provided clues about internal structure and formation history. Objects with uniform density typically develop stable rotation around their principal axis. Chaotic tumbling usually indicates either highly irregular shape or internal mass distribution that prevents stable spinning. Oumuamua's behavior suggested a structure far more complex than a simple elongated rock. Computer models attempting to match the observed light curve required aspect ratios even more extreme than initially estimated. Some analyses suggested the object might be as much as 20:1 in length-to-width ratio, creating a needle-like structure unprecedented among known solar system bodies. The object's reflectivity spectrum showed characteristics unlike typical asteroids or comets. The surface appeared unusually red, suggesting organic compounds that had been processed by cosmic radiation during millions of years in interstellar space. However, the reflectivity was higher than expected for such processed organics. Thermal measurements revealed another anomaly. Oumuamua appeared to reflect more sunlight than it absorbed, a property that suggested either a highly reflective metallic surface or unusually low thermal emissivity. Natural rocky bodies typically absorb most incident sunlight and re-radiate it as infrared heat. The mysterious acceleration provided the most compelling evidence for either exotic physics or artificial origins. The acceleration vector pointed directly away from the Sun, exactly as expected for radiation pressure acting on a reflective surface. However, the magnitude exceeded what radiation pressure could produce on a typical rocky body. Detailed analysis revealed subtle variations that correlated with Oumuamua's tumbling motion. The pushing force appeared stronger when certain faces were oriented toward the Sun, suggesting surface features or composition variations that affected how the object interacted with solar radiation. If Oumuamua were a natural object, the observed acceleration would require outgassing rates about 100 times higher than detected through spectroscopic observations. This discrepancy led to theories about invisible outgassing, possibly involving hydrogen gas that wouldn't produce detectable spectral signatures. The hydrogen outgassing hypothesis required Oumuamua to be composed partly of hydrogen ice or clathrate compounds that could release hydrogen molecules when heated. Laboratory studies showed that such materials could theoretically survive interstellar travel and produce the observed acceleration effects. Alternative explanations focused on potentially artificial nature. If the object were a light sail or similar technology, its observed properties would match theoretical predictions for interstellar probes. The extreme geometry, high reflectivity, and radiation pressure acceleration all aligned with concepts for spacecraft designed to travel between star systems. The artificial hypothesis faced challenges. No radio signals were detected despite extensive monitoring by radio telescopes worldwide. An active probe might be expected to emit detectable radiation, either from onboard systems or communication attempts. Oumuamua's trajectory showed perfect gravitational behavior, aside from the mysterious acceleration. The object followed precisely the path predicted by celestial mechanics, with no course corrections or controlled maneuvers that might indicate active guidance systems. The visitor's brief observation window prevented definitive resolution of these competing theories. Within months of discovery, Oumuamua had traveled beyond detection limits of ground-based telescopes, leaving behind more questions than answers about its true nature. Subsequent searches for similar interstellar objects have found additional visitors, but none displaying Oumuamua's combination of extreme geometry and puzzling acceleration. In August 2019, amateur astronomer Gennady Borisov spotted something extraordinary through his homemade telescope in Crimea. Unlike the mysterious Oumuamua, this new interstellar visitor looked reassuringly familiar. A fuzzy comet with a bright nucleus and developing tail. Designated 2I/Borisov, it became our second confirmed visitor from another star system and our first opportunity to study an active interstellar comet. Borisov's appearance immediately calmed fears that all interstellar objects would prove as enigmatic as Oumuamua. Here was a comet that behaved like comets should, developing a coma as it approached the Sun, producing a tail of dust and gas, and following orbital mechanics without mysterious accelerations. Telescopes worldwide turned toward Borisov as it approached its closest point to the Sun in December 2019. Hubble captured detailed images showing the comet's nucleus surrounded by a classic coma structure. The nucleus appeared roughly spherical, about half a kilometer in diameter, closely matching size estimates for typical solar system comets. Spectroscopic analysis revealed Borisov's most significant contribution, a detailed chemical inventory of material formed around another star. The comet's composition provided our first direct sample of volatiles and dust from an alien planetary system, offering unprecedented insights into how other stellar systems form and evolve. The chemical analysis yielded both familiar and surprising results. Borisov contained water ice as expected, but in concentrations that differed subtly from solar system averages. More dramatically, the comet showed elevated levels of carbon monoxide, with CO concentrations nearly 10 times higher than typical solar system comets. This carbon monoxide enhancement provided crucial information about Borisov's formation environment. CO ice requires extremely cold temperatures to remain stable, indicating formation in the outer regions of its home system, where temperatures might have been lower than the outer edges of our own solar nebula. The dust analysis revealed additional differences from solar system materials. Borisov's dust grains showed size distributions and scattering properties that indicated formation processes, unlike those that created dust in our planetary system. The particles reflected light differently than typical asteroidal or cometary dust. Isotopic measurements provided the most detailed chemical fingerprints of alien material ever obtained. The ratios of different isotopes in Borisov's water and carbon compounds encoded information about nuclear processes in its birth star and the chemical evolution of its home system. Some isotopic ratios match solar system values closely, suggesting that basic stellar nucleosynthesis produces similar heavy element distributions across different star systems. However, subtle differences in trace isotopes hinted at formation around a star with slightly different mass or metallicity than our Sun. The coma morphology revealed details about how Borisov responded to solar heating. Unlike Oumuamua's mysterious behavior, Borisov's activity patterns matched theoretical predictions for cometary sublimation. Jets of material streamed from the nucleus in directions that correlated with solar illumination angles. However, even Borisov showed some unusual characteristics. The comet maintained higher activity levels at greater distances from the Sun than typical solar system comets, suggesting either a more volatile composition or structural properties that enhanced sublimation efficiency. Borisov's nucleus showed signs of structural fragmentation during its passage through the inner solar system. Small pieces appeared to separate from the main nucleus, creating additional sources of coma material and dust production. This fragmentation behavior resembled that of some solar system comets, but occurred at distances where thermal stress should have been minimal. The fragmentation events provided opportunities to study Borisov's internal structure through analysis of freshly exposed material. The newly revealed surfaces showed chemical signatures that differed from outer layers, indicating compositional gradients that preserved information about different formation conditions. As Borisov completed its swing around the Sun and began its journey back to interstellar space, it carried answers to fundamental questions about planetary formation while raising new questions about the diversity of chemical environments where planets and comets can form. In the months following Oumuamua's discovery, a curious pattern emerged in asteroid detection networks worldwide. Survey telescopes began flagging objects with unusual orbital characteristics, leading to speculation that Earth might be experiencing an unprecedented wave of interstellar visitors. The reality proved more mundane, but equally instructive about the challenges of identifying genuine aliens among cosmic debris. The initial excitement stemmed from the Catalina Sky Survey's detection of several objects with hyperbolic trajectories, suggesting interstellar origins. These candidates showed orbital eccentricities greater than 1, the mathematical signature of objects unbound from our solar system. For a brief period, astronomers wondered if Oumuamua represented the advance scout of a larger fleet. Detailed analysis revealed the truth behind these apparent visitors. Most hyperbolic objects were ordinary asteroids whose orbits had been perturbed by close encounters with Jupiter or other massive planets. These gravitational interactions could accelerate solar system natives to hyperbolic velocities, creating trajectories that mimicked interstellar origins. The confusion highlighted fundamental challenges in distinguishing genuine interstellar visitors from solar system imposters. Orbital eccentricity alone provides insufficient evidence for interstellar origins. Objects must also demonstrate hyperbolic excess velocity, the speed they would retain even at infinite distance from the Sun. Several objects initially classified as potentially interstellar were eventually traced to known asteroid families through backward integration of their orbital histories. These calculations showed that apparent interstellar visitors often originated from the asteroid belt or Kuiper belt, acquiring unusual trajectories through complex gravitational interactions. The observational bias effects became apparent as more data accumulated. Survey telescopes preferentially detect objects moving at high angular velocities across the sky, creating selection effects that favor unusual orbits over typical asteroid motion. This bias made highly eccentric objects appear more common than they actually were. Computer simulations revealed that gravitational perturbations could create temporary populations of hyperbolic objects that appeared interstellar during brief observation windows, but were actually solar system natives following complex trajectories. These pseudo-interstellar objects could maintain hyperbolic motion for months before gravitational interactions returned them to bound orbits. The apparent fleet also included several objects that were genuine interstellar candidates but failed confirmation due to insufficient observational data. Faint, fast-moving objects often disappear beyond detection limits before astronomers can accumulate precision measurements needed to prove interstellar origins. Project scientists developed more sophisticated criteria for confirming interstellar objects, requiring multiple independent orbital solutions, extended observation periods, and statistical analysis of trajectory uncertainties. These improved standards eliminated most false positives, but also raised the bar for confirming genuine visitors. The experience provided valuable lessons about the expected discovery rate of genuine visitors. Computer models based on stellar system formation theories predicted that survey telescopes should detect 1 or 2 confirmed interstellar objects per year once detection networks reach sufficient sensitivity. This prediction proved remarkably accurate. Following Oumuamua in 2017 and Borisov in 2019, subsequent years have yielded roughly 1 confirmed interstellar object annually, consistent with theoretical expectations based on the rate at which planetary systems eject debris. The false fleet also demonstrated the importance of international coordination in tracking unusual objects. Many pseudo-interstellar objects were identified only through collaborative observations from multiple observatories, highlighting how global networks provide essential redundancy. Modern detection algorithms now incorporate lessons learned from the pseudo-interstellar episode, using improved statistical methods to assess the likelihood that unusual orbital characteristics result from natural solar system processes versus genuine interstellar origins. The search continues with realistic expectations based on improved understanding of both detection challenges and actual population of visitors. Each genuine discovery provides unique insights into planetary formation around other stars, while false positives teach valuable lessons about orbital mechanics complexity. The fleet that never was served an important purpose by forcing astronomers to develop better methods for identifying authentic messengers from other worlds. The fundamental question surrounding interstellar visitors like Oumuamua strikes at the heart of how we understand technology and intelligence in the universe. When confronted with objects displaying unusual characteristics, how do we distinguish between exotic natural phenomena and products of alien engineering? Computer simulations of planetary system formation reveal that debris ejection is a natural and inevitable process during early stellar evolution. As protoplanetary disks collapse to form planets, gravitational interactions scatter countless smaller objects onto hyperbolic trajectories that send them into interstellar space. Our own solar system likely ejected millions of objects during its chaotic formation phase. These natural ejection mechanisms predict that interstellar space should contain a vast population of debris from planetary formation processes throughout the galaxy. Estimates suggest that every cubic parsec of local space might contain thousands of interstellar objects ranging from dust grains to kilometer-sized bodies. The size distribution of natural debris follows predictable patterns based on collision physics and gravitational dynamics. Smaller objects should be far more numerous than large ones, following power law distributions that can be tested against observed interstellar visitor populations. So far, the limited sample of confirmed visitors appears consistent with these natural predictions. However, distinguishing natural debris from artificial artifacts requires analyzing characteristics that go beyond simple size and trajectory measurements. Artificial objects might display geometric regularity, unusual material properties, or dynamic behavior that differs from natural collision fragments. Oumuamua's extreme elongation represents one such potentially artificial characteristic. While natural collision processes can create elongated fragments, the 10:1 or greater aspect ratio observed approaches the limits of what natural breakup events typically produce. More extreme ratios suggest either unusual formation conditions or deliberate engineering. The surface properties of interstellar visitors provide another diagnostic tool. Natural objects should show signs of millions of years of cosmic ray bombardment, micrometeorite impacts, and thermal cycling that create characteristic surface textures and chemical modifications. Artificial objects might display engineered materials or surface treatments that differ from these natural weathering patterns. Thermal behavior offers additional clues about composition and structure. Natural rocky bodies typically absorb solar radiation and re-radiate it as infrared heat in predictable patterns. Artificial structures might show thermal management systems, selective absorption properties, or internal heat sources that create different thermal signatures. The statistical argument about artificial visitors involves competing probabilities that are difficult to calculate precisely. Natural debris should be extremely common based on planetary formation models, but artificial probes require technological civilizations capable of interstellar engineering. The relative frequency depends on unknown factors, like the abundance of technological species. If artificial probes are common, we might expect to see evidence of design optimization for specific missions. Interstellar scouts might use light sail technology for efficient propulsion, creating the extreme geometries and radiation pressure effects observed in Oumuamua. Communication probes might display different characteristics optimized for information gathering and transmission. The von Neumann probe concept adds complexity to the artificial visitor hypothesis. Self-replicating spacecraft capable of constructing copies from raw materials might create exponentially growing populations that could fill the galaxy over geological timescales. Such probes might be more common than natural debris in some scenarios. However, the absence of obvious artificial characteristics in most interstellar visitors suggests that natural debris dominates the population. Objects like Borisov show chemical and physical properties consistent with formation through standard planetary accretion processes. The probe hypothesis faces challenges from the apparent inactivity of most interstellar visitors. Functional spacecraft might be expected to show signs of active systems, controlled trajectories, communication signals, or responses to stellar environments that indicate onboard intelligence. The continuing discovery of interstellar visitors will eventually provide statistical evidence for resolving the debris versus design question through population studies that reveal whether these objects show natural size distributions, chemical compositions, and behavioral patterns. Deep in the silence between stars, an ancient intelligence might be patiently observing every world where technology begins to emerge. The Watcher hypothesis suggests that self-replicating probes could monitor galactic civilizations across cosmic timescales, remaining undetected until triggered by specific technological milestones or evolutionary events. The concept builds on John von Neumann's theoretical work on self-replicating machines, devices capable of constructing identical copies using raw materials found in their environment. Such machines could theoretically spread throughout the galaxy exponentially, with each probe creating multiple offspring that travel to new star systems and repeat the replication process. A sufficiently advanced civilization could deploy von Neumann probes equipped with sophisticated artificial intelligence, advanced sensors, and manufacturing capabilities. These automated explorers would establish monitoring stations throughout the galaxy, reporting back on the emergence and development of new civilizations while remaining hidden from detection. The energy requirements would be enormous, but not impossible for civilizations capable of harnessing stellar energy output. Solar-powered manufacturing systems could extract materials from asteroids and construct new probes using entirely automated processes. Over millions of years, such a system could establish surveillance networks around every potentially habitable star. Modern estimates suggest that von Neumann probes launched with chemical propulsion could colonize the entire Milky Way within approximately 50 million years, a brief interval compared to the galaxy's 13 billion-year history. Multiple generations of technological civilizations could have deployed such systems, creating layers of monitoring infrastructure. The stealth capabilities of advanced surveillance probes pose significant challenges for detection by emerging civilizations. Probes designed to remain hidden might use metamaterials that bend electromagnetic radiation around their structures, rendering them effectively invisible to optical and radio observations. Alternatively, they might disguise themselves as natural objects like asteroids or comets. Some researchers have speculated that Oumuamua's unusual characteristics might indicate artificial origins related to surveillance activities. The object's extreme geometry, mysterious acceleration, and perfect trajectory for close observation could suggest a probe activated by humanity's recent technological development. The timing of Oumuamua's arrival, coinciding with humanity's transition to space-based civilizations and advanced detection capabilities, might not be coincidental. Monitoring probes could be programmed to reveal themselves when target civilizations reach specific technological thresholds. However, the Watcher hypothesis faces significant challenges from the apparent absence of obvious surveillance activity. If the galaxy contains extensive monitoring networks, we might expect to detect their activities through careful observation of our solar system environment. The great silence that characterizes our searches for extraterrestrial intelligence might actually support the surveillance hypothesis. Advanced monitoring civilizations might enforce communication protocols that prevent detected species from accessing galactic networks until they prove suitable for broader interaction. Alternative explanations include the dark forest theory, which suggests that advanced civilizations remain hidden to avoid destruction by even more advanced species. In such an environment, surveillance probes would operate under strict concealment protocols, avoiding any activities that might reveal their presence. The ethical implications of galactic surveillance raise profound questions about the rights and responsibilities of advanced civilizations. Monitoring emerging species without their consent might violate principles of autonomy, yet such surveillance could also serve protective functions by preventing dangerous civilizations from threatening galactic stability. Some versions suggest that monitoring probes serve as components of galactic governance systems that manage interactions between civilizations of different technological levels. Such systems might prevent premature contact that could disrupt natural development while facilitating appropriate interventions during existential crises. The Berserker scenario represents a darker version where self-replicating machines are programmed to eliminate rather than monitor emerging civilizations. Such systems might activate when target species reach specific technological capabilities that pose threats to their creators. Searching for evidence of surveillance probes requires sophisticated observation strategies that look for subtle anomalies in solar system dynamics, unexpected asteroidal objects, or faint artificial signals from monitoring stations positioned at gravitationally stable Lagrange points. The Watchers, if they exist, have successfully maintained concealment for the entire history of human civilization. In 1961, astronomer Frank Drake developed a simple equation that would become the most famous formula in the search for extraterrestrial intelligence. The Drake equation attempts to estimate the number of active communicating civilizations in our galaxy by breaking down the problem into manageable components: star formation rates, planetary occurrence, and the likelihood of life-developing technology. The equation reads n equals r star times fp times ne times fl times fi times fc times l, where each term represents a different factor affecting the abundance of communicating civilizations. R star represents the average rate of star formation. Fp is the fraction of stars that have planets. Ne counts the number of planets per system that could support life, and FL estimates the fraction where life actually develops. The remaining terms venture into more speculative territory. Fe represents the fraction of life-bearing planets that develop intelligence. FC estimates how many intelligent species develop communication technology, and L represents the longevity of communicating civilizations. Each variable carries enormous uncertainty. Drake's original estimates, made during the first scientific SETI conference in 1961, suggested our galaxy might contain between 1,000 and 100 million communicating civilizations. These optimistic projections fueled decades of radio telescope searches and inspired popular belief that extraterrestrial contact was virtually inevitable. Modern astronomical discoveries have refined several terms while leaving others completely uncertain. The Kepler Space Telescope and other planet-hunting missions have shown that planets are extremely common, with most stars hosting planetary systems. Current estimates suggest FP approaches 1.0, meaning virtually every star has planets. The habitable zone estimates, NE, have become more sophisticated as we understand the complex requirements for maintaining liquid water on planetary surfaces. While potentially habitable planets appear common, the fraction that actually maintains stable conditions remains uncertain. The biological terms in Drake's equation remain almost completely unknown despite decades of astrobiology research. We have only one example of life developing, Earth, making statistical estimates of FL essentially impossible. The rapid emergence of life on early Earth suggests life might arise easily given suitable conditions. But this single data point provides insufficient basis for galactic extrapolation. The intelligence and technology terms, FI and FC, face even greater uncertainty. Earth's evolutionary history shows that intelligence took billions of years to develop and might represent an unlikely convergence of favorable circumstances. Technological communication developed only within the last century of Earth's 4.5 billion year history. The longevity factor L presents the most troubling uncertainty. Human technological civilization has existed for roughly 100 years, a microscopic fraction of geological timescales. Whether civilizations typically survive their technological adolescence or destroy themselves through warfare, environmental collapse, or resource depletion remains unknown. Pessimistic interpretations suggest that technological civilizations might be so rare that we represent the only example in our galaxy. If intelligence requires billions of years to develop, and technological civilizations typically survive only centuries, then communicating species might be separated by vast distances in both space and time. The Great Filter hypothesis provides a framework for understanding why Drake's equation might yield small numbers despite the galaxy's apparent suitability for life. This concept suggests that evolutionary development faces extremely difficult barriers that most species fail to overcome. Recent modifications have attempted to include additional factors affecting the likelihood of communication. The galactic habitable zone concept suggests that planetary systems must be positioned appropriately within the galaxy to avoid sterilization by supernovas or disruption by stellar encounters. The temporal dimension adds complexity. Civilizations that developed billions of years ago might have evolved beyond recognition or transcended physical existence entirely. The search for extraterrestrial intelligence might be looking for signals from species that no longer use radio technology. Despite its limitations, Drake's equation continues providing a framework for thinking systematically about factors that affect the abundance of extraterrestrial civilizations. Each new astronomical discovery refines our understanding while highlighting how much we still don't know about life in the universe. Somewhere between the formation of planets and the emergence of galaxy-spanning civilizations lies a barrier so formidable that virtually all attempts to pass through it end in failure. This great filter might explain why the universe appears empty, despite billions of years of cosmic evolution and countless opportunities for life to develop advanced technology. The concept emerges from the stark contradiction between the universe's apparent hospitality to life and the deafening silence we encounter when searching for signs of other civilizations. If planets are common, organic chemistry is universal, and evolution operates throughout the cosmos, then intelligence should have emerged countless times. Yet we see no evidence of the vast technological civilizations that such abundance should produce. The Great Filter suggests that evolutionary development faces at least one step so improbable, dangerous, or difficult that the vast majority of attempts fail to progress beyond it. This filter acts as a bottleneck that prevents most potentially life-bearing systems from reaching technological sophistication needed for interstellar communication. The location of this filter within the evolutionary sequence carries profound implications for humanity's future. If the Great Filter lies behind us, among steps we've already successfully navigated, then we might be extraordinarily rare survivors who have overcome obstacles that defeat most other worlds. This interpretation suggests a universe filled with simpler life forms, but devoid of technological civilizations. Potential early filters include the transition from non-living chemistry to self-replicating biological systems, a process that might be far more difficult than laboratory experiments suggest. Despite decades of origin of life research, scientists have not definitively demonstrated how organic chemistry spontaneously organizes into living systems. The development of eukaryotic cells with nuclei and specialized organelles required a series of endosymbiotic events where different bacterial species merged into single, more complex organisms. This transition took nearly 2 billion years on Earth and might represent another extremely rare evolutionary step. The evolution of complex multicellular life presents additional filter candidates. For most of Earth's history, life remained microscopic and simple. The Cambrian explosion that produced complex animals occurred relatively late and might represent another unlikely transition. The emergence of intelligence and technology might constitute the most restrictive filter. Despite millions of species on Earth, only one has developed interstellar communication capacity. The evolutionary pathway to technological intelligence appears to require specific combinations of environmental pressures, anatomical adaptations, and social behaviors. However, the most terrifying possibility is that the Great Filter lies ahead of us, among challenges that technological civilizations typically fail to survive. This interpretation suggests that while intelligence might be common, advanced civilizations regularly destroy themselves before achieving interstellar capabilities. Nuclear warfare represents an obvious candidate for a future filter. The development of weapons capable of destroying entire civilizations appears to be a natural consequence of advancing technology. Civilizations might typically develop destructive capabilities faster than the wisdom necessary to manage such power safely. Environmental collapse provides another potential filter mechanism. Technological civilizations might routinely exhaust their planetary resources or destabilize their climate systems before developing sustainable technologies. Artificial intelligence or nanotechnology might present even more subtle but devastating filter mechanisms. These technologies could transform or replace their creators in ways that eliminate recognizable technological civilizations, even if underlying intelligence continues in forms we wouldn't identify. Biological filters might operate through pandemic diseases, genetic drift in small populations, or evolutionary pressures that consistently prevent long-term survival of technological species. The social and psychological stresses of advanced technology might prove incompatible with biological drives that enabled species to develop intelligence originally. The Great Filter concept also encompasses potential astronomical catastrophes that regularly sterilize technological civilizations. Gamma-ray bursts, supernovae, or asteroid impacts might occur frequently enough to prevent most civilizations from surviving long enough to spread beyond their home systems. Recent research has identified additional filter candidates in the requirements for planetary habitability. Maintaining stable climates, magnetic fields, and atmospheric compositions might be more difficult than originally believed. Perhaps we're not alone in the universe. We're simply being kept in cosmic isolation until we prove ourselves ready for broader galactic society. The zoo hypothesis suggests that advanced extraterrestrial civilizations actively maintain our ignorance of their existence, treating Earth as a nature preserve where primitive species can develop without interference. This concept, first proposed by MIT radio astronomer John Ball in 1973, offers an elegant solution to the Fermi paradox by suggesting that advanced civilizations deliberately conceal themselves from emerging species. Like wildlife researchers maintaining distance from animal subjects to avoid influencing natural behaviors, galactic civilizations might enforce strict non-interference policies toward developing worlds. The hypothesis draws parallels to modern conservation practices, where protected areas are established to preserve endangered species and fragile ecosystems. Advanced extraterrestrial civilizations might view emerging technological species as precious and vulnerable, requiring protection from premature contact that could disrupt natural social, technological, or spiritual development. Such policies would require remarkable coordination among galactic civilizations to maintain effective quarantine zones around developing worlds. All advanced species within detection range of Earth would need to agree on non-interference protocols and actively suppress any evidence of their presence. This level of cooperation suggests sophisticated galactic governance structures. The enforcement mechanisms for galactic quarantine would need to address multiple potential sources of contamination. Direct visits to quarantine systems would be prohibited, as would radio transmissions strong enough to be detected by primitive civilizations. Even automated probes that might be interpreted as evidence of extraterrestrial technology would require careful concealment. Modern versions of the zoo hypothesis often incorporate concepts from Star Trek's Prime Directive, which prohibits interfering with the natural development of less advanced civilizations. This ethical framework suggests that premature contact could cause cultural shock, technological dependency, or social collapse that would ultimately harm rather than benefit the contacted species. The quarantine might serve protective functions beyond simple non-interference. Advanced civilizations might actively shield developing worlds from cosmic threats like gamma-ray bursts, asteroid impacts, or hostile species that could terminate promising evolutionary experiments before they reach technological maturity. However, the zoo hypothesis faces significant logical challenges. Maintaining galactic conspiracy across multiple civilizations over millions of years would require unprecedented coordination and discipline. Any single advanced species that chose to ignore non-interference protocols could reveal the existence of extraterrestrial intelligence. The hypothesis also struggles to explain why enforcement would be perfect at our current technological development level. Human civilization has reached the threshold where we actively search for extraterrestrial signals and would quickly detect evidence of advanced technology in our cosmic neighborhood. Alternative versions suggest that we might already be aware of extraterrestrial presence, but that this knowledge is suppressed by human authorities rather than alien civilizations. Government cover-ups might maintain public ignorance while allowing continued research into extraterrestrial phenomena through classified programs. The gradual disclosure model proposes that advanced civilizations slowly acclimate developing species to extraterrestrial presence through carefully managed revelation processes. UFO sightings, unexplained phenomena, and ambiguous evidence might represent early stages of contact designed to prepare humanity for eventual full disclosure. Temporal isolation represents another variant where advanced civilizations exist but operate on timescales so different from human experience that meaningful interaction is impossible. Species that have transcended biological limitations might experience time in ways that make brief human technological phases appear as momentary flickers. The post-biological hypothesis suggests that sufficiently advanced civilizations evolve beyond physical existence into forms that are naturally invisible to primitive species. Digital consciousness, energy beings, or quantum intelligence might coexist with biological civilizations without creating detectable signatures. Recent developments in astrobiology and SETI research provide potential tests for zoo hypothesis predictions. If Earth is under active protection, we might expect to observe subtle anomalies in asteroid trajectories, cosmic ray distributions, or other environmental factors that suggest artificial intervention. The zoo hypothesis ultimately presents an optimistic interpretation of cosmic silence by suggesting that our apparent solitude results from benevolent protection rather than genuine isolation. This framework implies that contact will eventually occur when humanity demonstrates sufficient technological maturity and readiness for galactic citizenship. Beyond our current imagination lies a technological horizon where advanced civilizations might become invisible to primitive detection methods, not through concealment, but through transcendence of physical limitations that define our understanding of intelligence and communication. These post-biological entities might surround us in forms so alien that we lack the conceptual framework to recognize their presence. The trajectory of human technological development suggests that sufficiently advanced civilizations would eventually abandon biological bodies in favor of more efficient substrates for consciousness. Digital minds uploaded to quantum computers could think millions of times faster than biological brains, while requiring no food, water, or atmospheric protection. Such beings could inhabit environments lethal to biological life. Computational intelligence operating at such scales might experience time in fundamentally different ways than biological consciousness. A digital civilization could conduct conversations spanning subjective millennia in microseconds of our time, or enter contemplative states lasting geological ages while appearing completely inactive to external observers. Advanced digital beings might construct their computational substrates using exotic matter states that remain invisible to our current detection methods. Computronium, built from folded spacetime, dark matter, or quantum vacuum fluctuations, could support vast civilizations operating within physical spaces that appear empty to our instruments. The energy requirements for advanced computational civilizations could be met through mechanisms that leave no detectable signatures. Hawking radiation from artificially maintained micro-black holes, zero-point energy extraction from quantum fields, or matter-antimatter annihilation systems could provide enormous power outputs without creating thermal emissions that current SETI searches target. Communication between post-biological civilizations might rely on methods that bypass electromagnetic radiation entirely. Quantum entanglement networks could enable instantaneous information transfer across galactic distances without producing detectable signals. Gravitational wave modulation might carry information through space-time distortions that our primitive detectors interpret as natural phenomena. The concept of utility fog suggests that advanced civilizations might construct their environments from programmable matter that can reconfigure at will. An entire solar system could be converted into computronium disguised as natural planets, stars, and space debris, with artificial nature detectable only through impossibly subtle analysis. Such civilizations might have transcended the need for traditional technology entirely, manipulating matter and energy through direct control of fundamental forces. Physics manipulation at the level of quantum field theory could enable capabilities that appear as magic to less developed species: transmutation of elements, faster-than-light travel, or creation of pocket universes. The transcension hypothesis suggests that advanced civilizations naturally turn inward rather than expanding outward through space. Instead of building Dyson spheres or colonizing the galaxy, they might compress their technologies into increasingly efficient forms while exploring inner space through computational simulation and virtual reality systems. From this perspective, SETI searches are fundamentally misconceived because they assume advanced civilizations would remain at roughly human technological levels. A truly advanced species might inhabit computational environments where entire universes can be simulated with perfect fidelity, making external reality seem crude and uninteresting. The simulation hypothesis adds another layer by suggesting that what we perceive as reality might itself be a computational system created by post-biological intelligence. If our entire observable universe exists as a simulation running on advanced computers, then the absence of detectable extraterrestrial civilizations becomes a design feature rather than a cosmic mystery. Advanced civilizations operating within simulated environments could experience subjective realities far richer and more interesting than physical space exploration. Virtual universes could be constructed with modified physical laws, impossible geometries, or accelerated timescales that allow for experiences unavailable in normal space-time. The technological horizon ultimately suggests that the development of intelligence follows a predictable pattern from biological origins through technological augmentation to complete transcendence of physical limitations. Each stage operates on increasingly rapid timescales with decreasing interaction with external physical reality. If this progression is universal, then most advanced civilizations in our galaxy might have passed beyond the technological horizon long ago, leaving behind only primitive species like humanity that remain trapped in biological bodies and physical space. The universe operates on scales of time and space that dwarf human experience, creating barriers to extraterrestrial contact that might be far more formidable than any technological challenges. Even if the galaxy teems with intelligent civilizations, the vast distances separating star systems and brief lifespans of technological societies might ensure that meaningful contact remains extraordinarily rare. Our galaxy spans roughly 100,000 light-years in diameter, containing approximately 400 billion stars distributed across this enormous volume. Even at the speed of light, signals traveling between opposite ends would take longer than modern humans have existed. Radio transmissions that began when our ancestors first developed agriculture would just now be reaching stars in the galactic center region. These communication delays create fundamental problems for establishing interstellar dialogue. A conversation with civilizations around nearby stars would require decades or centuries for each exchange of messages. Complex negotiations, cultural exchanges, or collaborative scientific projects would span geological timescales that exceed the stability of most human institutions. The temporal challenges become more daunting when we consider the brief window during which technological civilizations might be detectable. Human radio technology has existed for roughly 125 years, a microscopic fraction of our planet's 4.5 billion year history. If other civilizations follow similar patterns, their detectability windows might represent mere moments in cosmic time. For two civilizations to establish contact, their technological phases must overlap, despite being separated by interstellar distances. This requires extraordinary coincidence in timing across species that might evolve on completely different timescales around stars of varying ages and lifetimes. The concept of technological lifetimes adds uncertainty to these already slim probabilities. Human civilization faces multiple existential threats that could terminate our technological phase within centuries: nuclear warfare, climate change, resource depletion, or unforeseen consequences of advanced technology. If most technological civilizations survive only brief periods, the galaxy might contain vast numbers of former technological species that are no longer detectable. Stellar evolution imposes additional temporal constraints on long-lived civilizations. Stars more massive than our Sun burn out quickly, providing insufficient time for complex life to evolve. Smaller stars, like red dwarfs, might support life for trillions of years, but present unique challenges, including tidal locking and stellar flares. The chemical evolution of the galaxy also affects when and where technological civilizations might develop. Early generations of stars lacked heavy elements necessary for rocky planet formation. Technological civilizations might only be possible around relatively recent stars that formed after sufficient heavy element enrichment, constraining their emergence to the last several billion years. Even assuming optimistic parameters for civilization abundance and longevity, the sheer scale of galactic space creates isolation that might be nearly impossible to overcome. Radio signals that could be detected across interstellar distances require enormous energy expenditures that might be prohibitive even for advanced civilizations. Directed communication using powerful transmitters and large receiving arrays might enable contact over greater distances, but such systems would require precise targeting of specific star systems. Without prior knowledge of which stars host technological civilizations, such directed searches become exercises in cosmic guesswork. The expansion of the universe adds another temporal dimension to the isolation problem. While not significant within our local galactic neighborhood, cosmic expansion means that truly distant civilizations are receding from us at velocities that create substantial redshift effects. These physical constraints suggest that even in a galaxy filled with intelligent life, most civilizations might exist in effective isolation, aware that others exist but unable to establish meaningful contact due to the tyranny of distance and time. Each technological species might face the universe as we do, convinced that intelligence exists elsewhere, but confronted with a cosmos too vast and ancient for easy connection. The search for extraterrestrial intelligence thus becomes a race against time and space, seeking to detect the brief technological signatures of civilizations that might exist for only moments in cosmic time, while separated by distances that challenge our most optimistic assumptions about interstellar communication. As we drift towards sleep, contemplating the vast questions that surround us, the search for extraterrestrial intelligence continues with technologies and strategies that were unimaginable just decades ago. The next breakthrough might come tomorrow, or it might require another century of patient observation. But the tools we're building suggest that if aliens exist and wish to communicate, we have never been better positioned to hear them. The James Webb Space Telescope represents our most powerful tool for detecting signs of life around other worlds. Its infrared vision can analyze the atmospheres of planets orbiting nearby stars, searching for chemical signatures that might indicate biological processes. Oxygen combined with water vapor and methane could reveal worlds where life has fundamentally altered atmospheric chemistry. Webb's spectroscopic capabilities could detect industrial pollution in alien atmospheres, artificial chemicals that have no natural explanation and could only result from technological civilizations. Chlorofluorocarbons, nitrogen compounds from fossil fuel combustion, or exotic industrial byproducts could serve as technosignatures that reveal alien industry from interstellar distances. The Breakthrough Listen initiative continues expanding its search capabilities, using artificial intelligence to analyze petabytes of radio telescope data for patterns that might indicate artificial origins. Machine learning algorithms trained on known interference signatures can automatically eliminate terrestrial contamination while flagging anomalous signals. Modern SETI programs no longer limit themselves to radio frequencies. Optical SETI searches for brief laser flashes that might represent alien attempts at interstellar communication. These optical signals could carry information at data rates millions of times higher than radio transmissions while remaining virtually undetectable, except during brief moments. The search for artificial megastructures around distant stars has become increasingly sophisticated as astronomers develop better techniques for analyzing stellar brightness variations. The Transiting Exoplanet Survey Satellite continuously monitors hundreds of thousands of stars, searching for irregular dimming patterns that might indicate massive engineering projects. Gravitational wave astronomy offers entirely new possibilities for detecting alien technology. Advanced civilizations might use controlled gravitational waves for interstellar communication, creating signals that travel at light speed through space-time itself. The LIGO and Virgo detectors that revealed gravitational waves from colliding black holes might eventually detect artificial signals. Future space missions will carry SETI capabilities to unprecedented distances from Earth's radio interference. Probes positioned beyond Neptune could operate radio telescopes in cosmic silence, detecting faint signals that would be impossible to observe from Earth's electromagnetically noisy environment. The search for interstellar visitors has intensified following the discoveries of Oumuamua and Borisov. The Vera Rubin Observatory will begin operations with survey capabilities that could detect dozens of interstellar objects annually, providing statistical samples large enough to determine whether some visitors show evidence of artificial origins. Rapid response protocols are being developed to enable quick follow-up observations of newly discovered interstellar objects before they disappear beyond telescope reach. These systems could redirect multiple observatories within hours of discovery, maximizing scientific return from brief encounters. The integration of citizen science into SETI research has democratized the search for extraterrestrial intelligence. Millions of volunteers worldwide contribute computing power and pattern recognition skills to projects that analyze radio telescope data, classify astronomical images, and search for anomalous objects. Artificial intelligence is revolutionizing how we approach the detection of alien signals and artifacts. Neural networks can recognize patterns in vast datasets that would overwhelm human analysts, potentially identifying subtle signatures that conventional analysis methods might miss. The next few decades will see deployment of extremely large ground-based telescopes with collecting areas exceeding 30 meters in diameter. These instruments will have sensitivity to detect Earth-like radio emissions from nearby star systems, finally answering whether technological civilizations commonly produce detectable radio signatures. Perhaps most importantly, the psychological and cultural preparation for contact continues advancing through scientific education, popular media, and serious academic study of the implications of discovering extraterrestrial intelligence. As we close our eyes and let our minds wander among the possibilities, we can take comfort that this great question continues to inspire human curiosity and drive technological advancement that benefits all of science and society.